Good morning. My name is Matthias Fresacher, and today I'm going to tell you about joint work I did together with Willow, Stewart and Danny Tubbenhauer on working towards post-quantum cryptography using diagram monoids and their representations. To begin with, some motivation. Symmetric key cryptography has been around for millennia, but unfortunately suffers from man-in-the-middle attacks, as this illustration shows. This was not overcome until 1976 with the advent of public key cryptography, which again, now as the illustration shows, is able to overcome man-in-the-middle attacks. Within these commonly used encryption schemes lies a platform monoid. Now classically, this has been an abelian group. However, Shor's algorithm published in 1994 is able to feasibly speed up a brute force attack to make it fast enough to break these commonly used encryption schemes. However, it does require a quantum computer to run. Whilst they don't exist just yet, they are right around the corner, so we do need to get ready for them now. To that end, it has been proposed to make use of a non-commutative monoid as a platform monoid instead, because Shor's algorithm simply does not apply to it. But this is not the only attack we need to guard against. We also need to protect against linear attacks. For clever protocol designs, the abelian group is able to slow down a linear attack to make it practically infeasible. But unfortunately, the non-commutative monoids are susceptible to linear attacks. And this is where the notion of a RepGap comes in. Specifically, it measures the resistance to a linear attack. Formally, it's the size of the smallest non-trivial representation of the monoid. So we can see if we are to increase the RepGap to be large enough, we're able to slow down a linear attack to make it infeasible. And that's the key question that this project tackled. Can twistings increase the RepGap of diagram monoids? So let's get into the details. Obviously, the main object of study are diagram monoids, and we're mostly going to focus on the partition monoid Pn. Formally speaking, its elements are the partition of this particular set, but they are called diagram monoids for a reason, and that is because we can picture them graphically as two rows of vertices where we might have some non-transversal edges, and we may have some transversal edges linking the top and the bottom rows. We're also going to be interested in a number of submonoids of the partition monoid, specifically Templey-Lieb. So it has the condition that its diagrams must be planar. By that I mean the edges are not allowed to cross like they do up here. The graph must be planar. And we also have the condition that every block in our graph must have size exactly 2. We can talk about the degree of an entire monoid, and this simply counts the number of vertices in our row. So both of these belong to a monoid of degree 5. We can also talk about the rank of a specific diagram, and this counts the number of transversal edges. Here we have one transversal edge. This diagram has got rank 1. Here we have 1, 2, 3. This diagram has got rank 3. Concatenation, well, that's the multiplication operation of our monoid. And I'm going to start off with the non-twisted concatenation. For those of you that are visual-based learners, this is an animation of that procedure in action. And for everybody else, I'm going to make use of this intermediary step to explain to you how we end up at the concatenated diagram. First, we position the diagram one directly underneath the other, and then we draw these red vertical in-between edges. We then remove the two inner rows of vertices, and we remove any floating components that are created. So in black, we have a floating component, any edge that is not connected to the top or bottom row of vertices. And then we just tidy up what we have left. This is an associative operation. We do have an identity diagram, specifically just all vertical edges, but it is not a commutative operation. We're also going to be interested in the zero-twisted version of the partition monoid, which is the ordinary partition monoid, but joining on a 0. And we're also going to need to update our non-twisted concatenation to now be the zero-twisted concatenation. This is essentially the same as our non-twisted concatenation, except of removing floating components. Now we're going to count our floating components. And the map phi is going to keep track of that count of the number of floating components. So if phi is strictly greater than 0, then our product is just going to be 0. Here phi is equal to 1, so in the zero-twisted concatenation, our product is now 0. Otherwise, we tidy up like we did before. So our overarching question was, can twistings increase the RepGap of diagram monoids? Well, to be able to answer that, we obviously need to be able to compute the RepGap. Unfortunately though, in general, this is a hard thing to do, but it is easy if the monoid is H-trivial. In that case, all we need is the rank of the Graham matrix to be able to compute the RepGap. For the diagram monoids, being H-trivial is the same as being planar, hence why Templey-Lieb is a good example to keep in mind. So then our objective of increasing the RepGap is going to become increasing the rank of the Gram matrix. What is the Gram matrix? Well, let's take a look at a D-class in our egg box picture and associate to it a matrix. And we're going to be interested in the idempotents. So in red here is all of the H classes that contain an idempotent. And for each of these H classes, I'm going to put a 1 in my Gram matrix and 0 otherwise. So this is my Gram matrix. So the objective sounds pretty simple, maximize the rank of a matrix. But rank is a bit of an opaque object. It's not just the number of idempotents that matter, but also their exact and relative positions. If we now look at an example of, say, Templey-Lieb 6, this is what its egg box diagram looks like. And in red, we have all of the idempotents. So a prototypical example coming from the corner here would look like this. But we can see here we have two floating components being created. This is not going to be an idempotent in the zero-twisted concatenation. In fact, if we look at zero-twisted Templey-Lieb, its egg box diagram is exactly the same as the non-twisted version, except we have a 0 at the bottom. If we now look at the idempotents of the zero-twisted version, excluding 0, they're going to be a subset of our non-twisted idempotents. Specifically, these are the idempotents that survive. If we look at a prototypical example from here, we can see we sort of have a zigzagging of our edges. And this is how we prevent floating components from being created. So if I've only talked about zero-twisted objects, I now want to expand that to arbitrary twistings. And for that, I need to introduce some terminology. So I'm going to talk about the underlying monoid S, and this is going to be written multiplicatively. I then need a twisting map phi, which needs to satisfy this identity. For the diagram monoids, the number of floating components that I already introduced to you is a good example of this. And then we have our twisting monoid M, which I'm going to write additively, and it has to be commutative. We then pick an element Q in our twisting monoid M, and then we can define our twisted product T. So it has as its underlying set M cross S. A multiplication is given by this formula, but we don't need to know any details about the multiplication for the results I'm about to present. So let's get into those main results, starting off with the semigroup theory result. So if I take an arbitrary twisted monoid T, it does have to be tight, which unfortunately I don't have time to explain or define for you, where M is D-trivial. If we look at a D-class in the arbitrary twisted monoid, it needs to contain at least one idempotent, and I plus Q has to be an idempotent in M. If these are satisfied, then one or possibly both of the following two conditions are going to hold. If I look at the Gram matrix of the arbitrary twisted D-class, that is going to be the same as the Gram matrix of the corresponding non-twisted D-class. Or alternatively, that Gram matrix is going to be the same as the Gram matrix of the zero-twisted version of that D-class. We can do a little bit better than that. Precisely one of these holds if and only if there exists an idempotent in the non-twisted D-class, such that phi of that idempotent is strictly greater than 0. So what is this theorem telling us? Well, if I have an arbitrary twisted monoid T, to construct it I would have needed to have some twisting map phi. I would have had some twisting monoid M, for which I would have had lots of different choices. And within each M, I would have had lots of different choices for that parameter Q. All up, a huge number of choices. But the theorem is telling us, well, in fact, all of these choices boil down to just two. The non-twisted version and the zero-twisted version. In essence, all of these choices for M and Q kind of do not matter. There's also a representation theory result, and this is true for the following diagram monoids. Now don't worry if you're not familiar with all of them in detail, just think of partition or Templey-Lieb. So for the partition, partial Brouwer, symmetric inverse, Motzkin, Templey-Lieb, and order-preserving monoids, it holds that the representation gap of the non-twisted version of them is essentially the same as the representation gap of the zero-twisted version. Now I know essentially is a little bit hand-wavy, but I don't want to go into more detail than that. So if we now combine both of these results together, what have we got? Well, for the tight diagram monoids, so that is excluding partial Brouwer, Motzkin, and order preserving, it holds that the representation gap of any arbitrary twisting of it is essentially the same as the representation gap of the non-twisted version. So to conclude, can twistings increase the RepGap of the diagram monoids? Well, if I take an arbitrary twisted diagram monoid T, we know that we have many choices for that but by our semigroup theory result, we actually just have two choices, and by representation theory result, we only have one choice. So the answer is no. Or can they? Because this conclusion assumes that the hypothesis of the semigroup theorem holds. But this is actually a very strong condition that doesn't hold very often in general. But this does actually give us some hope. And this is in ongoing work that we're trying to exploit. And I just want to give you a sense of what we are hoping to achieve. So this is for a twisting monoid M of, say, 5 elements with some very exotic addition. And we're going to need some very specific choices for our parameter Q and our twisting map phi. But suppose we have those. And for this example, I'm just going to look at Templey-Lieb 5. So this is the egg box diagram that we would have. We can see we have a copy of Templey-Lieb 5 for each of our elements in our twisting monoid M. On the left, we have the zero twisted version, and on the right, we have the non-twisted version. And underneath here, I'm just going to write the number of idempotents in the bottom D class. So now let's suppose the hypothesis of the theorem holds. Then if we say look at this middle D class here, then it has to be either exactly the same as a non-twisted version or the zero twisted version. It can't be anything else, nothing in between. But if we now suppose that the theorem does not hold, well, at least conceivably, it is possible to achieve any number of idempotents between the two endpoints in the middle here. And this is what we are hoping to achieve to maximize the rank of the gray matrix as much as possible. So what does the future hold? Well, there is this outstanding work. So for this, we need to find suitable choices for our twisting monoid M and the twisting map phi. We are going to try and find these using a computer search. And as part of that, we will also looking to publish the gap code for our implementation of a arbitrary twisted monoid, which we plan on adding to the semigroups package. We're also working on a semigroup theory paper, which explores tightness, which unfortunately I've not had much time, in fact any time, to explain or define for you, but it's become quite the important property for these sort of twisted monoids. And there's also quite a large collection of other results that we have developed as part of this project that are of independent interest for semigroup theorists. And we're working on developing a diagram monoid-based encryption protocol. Towards further afield into the future, we also want to explore links to the well-studied Hecke algebras and specifically generalizations of these. And we're going to do this, or at least hoping to do that, via colored diagram monoids. This is a separate research project, but is joint work between myself and Mengfan Liu. If I now go back to the start where we had our encryption timeline, hopefully we're able to develop diagram monoid-based encryption protocols before quantum computers arrive so that we can stay secure well into the future.